This is our atomic absorption spectrometer. This compartment here houses the hollow cathode lamp, which is the light source for the spectrometer. The central part of the instrument houses the flame. Currently this is an acetylene oxygen flame burning at about 1000 degrees centigrade. And the sample, dissolved in water or acid, travels up this little tube here and then on upwards into the flame. The light from the hollow cathode lamp passes through the flame into this section of the instrument where we have the detector. It's not just the electrons of the atom that can be used for analysis. We can also use the nucleus of the atom. And this is the basis of a technique called neutron activation analysis. In this technique, we need to irradiate the sample with neutrons. The neutrons hit the nucleus of the atoms in the sample. And just as the electrons were put into excited states, the nucleus is also excited. It becomes a compound nucleus. This compound nucleus then decays, giving out a gamma ray, and typically will become a radioactive nucleus, which can then give out a gamma ray later on. And it will ultimately end up as a product nucleus. Just as the radiation given out by the electrons was characteristic, so the gamma rays given out by these nuclei is also characteristic. So if we measure the energy of the gamma rays given out, we can once again analyze the element. So it's a good technique in that it is non-destructive of your sample, but it does have a serious disadvantage in that in order to get the neutrons to do this analysis, you do need to have a nuclear reactor. If you don't have a nuclear reactor, then you really can't do this method. So the output from neutron activation analysis looks like this. On the x-axis, this is the energy of the gamma rays given out, and you can see that different elements give quite distinct peaks. So this particular sample here, which is an archaeological sample, contains elements such as scandium, iron, cobalt, sodium, and some other minor elements as well. Now, sometimes forensic scientists need to analyze objects that are extremely small. For instance, gunshot residue. This is particulate matter given out when firearms are fired. And these are particles which are maybe 5 micrometers across, far below what can be seen normally. So in order to visualize these objects, you have to use a scanning electron microscope. Now, a scanning electron microscope uses electrons instead of light, which is what normal microscopes use. So in a scanning electron microscope, there is an electron gun which fires a beam of electrons at the object of interest. These electrons hit the object and then they bounce off where they are detected. And it's the signals from the detector that are used to generate the image, like the image shown here. Now, when these electrons hit the sample, they can not just bounce off. They can also hit the atom and cause an electron to be ejected from that atom. When an electron is ejected from low down in the energy levels of the atom, it means that an electron higher up in the atom is going to drop down to fill that vacancy. Of course, as we know, when the electron drops down to this lower energy level, it must give out energy in the form of electromagnetic radiation. Now, typically, The kinds of drops that the electrons will do with this technique, these are big drops. They're dropping from a high energy level down to a much lower energy level. That means the radiation given out is high energy, and it typically corresponds to X-rays. And of course, these X-rays are characteristic of the particular element. So this technique is called energy dispersive X-ray fluorescence, or EDX. And because it is combined with the scanning electron microscope, we have what we sometimes call a hyphenated technique. And this technique, SEM-EDX, is very powerful for forensic science, because the SEM part, the microscopy, allows forensic scientists to look at extremely small objects. And the EDX part allows them to analyze the objects at the same time. So a SEM-EDX spectrum looks something like this, where on the x-axis we're looking at the energy of the emitted X-rays, and you can see we get peaks for the different elements. So this particular sample here has relatively large amounts of nickel and chromium, and smaller amounts of a range of other elements. Napoleon had a remarkable career. He started out as an ordinary artillery officer in the French army. He rose through the ranks to become a general. He became dictator of France. He then promoted himself to Emperor of France, and at the same time controlled most of the continent of Europe. He spent most of his career fighting wars, and he was finally defeated in 1815 at the Battle of Waterloo. After that battle, he went into exile, and the British sent him into exile as far away as possible to the little island of St. Helena down in the South Atlantic. And he lived out the last years of his life on St. Helena, dying in 1821. When he died, he was in his 50s. And for someone who had a fairly tough life riding around battlefields in the early 19th century, that was quite a respectable age. But even so, after his death, rumors started to go around that his death may not have been entirely natural. But there was no way to confirm or deny these rumors. There was no evidence. And Napoleon's body had eventually been taken back to France and been given a grand funeral, and nobody's going to be allowed to open up his tomb to do an analysis. However, we do have some artifacts from Napoleon. We have some samples of his hair. It was a rather strange fashion back in those days that when anyone famous was dying, after they died, some of their hair would be snipped off and kept as a souvenir. So you can imagine Napoleon lying there on his deathbed, surrounded by his courtiers and his doctors and his attendants, all of them with a pair of scissors ready, waiting for the last moment. Well, back in 1952, some of these hair samples were analyzed using neutron activation analysis. And from the results of that analysis, it was claimed that arsenic was present in the late emperor's hair. The obvious conclusion then, if there's arsenic in Napoleon's hair, Napoleon was murdered by arsenic poisoning. Well, if there's a murder, what's the motive? And certainly there were many people in the world who would have a motive for getting rid of Napoleon. The British, for instance, had spent many years and a vast amount of money in fighting the Napoleonic Wars to break this man's control of Europe. While the French government of the time was made up of all Napoleon's enemies, who really would not want him to come back. So if you're looking for a motive in murdering the emperor, they're not hard to find. Now, some years later, a British chemist called David Jones asked a very interesting question. He asked the question, what colour was Napoleon's wallpaper? Now, he happened to ask this question on a radio show, and one of the listeners contacted the radio station and said they knew what colour Napoleon's wallpaper was. And not only did they know what colour the wallpaper was, they actually had a piece of the wallpaper. Well, this seems very strange at first, until you realize the special position of the island of St. Helena. Before the construction of the Suez Canal, any ship sailing from England to India or Australia or to Singapore or other parts in the Far East would call in at St. Helena, mainly to get fresh food and fresh water to continue the voyage, but also to give any passengers on the ship the chance to get on dry land and stretch their legs. So in those days, the island of St. Helena would actually have quite a lot of visitors, many more than it does nowadays. Now, St. Helena is not rich in tourist attractions, but of course one of the tourist attractions is the house that Napoleon used to live in. And back in the early 19th century, the souvenir shop had not yet been invented. So these visitors to the island would help themselves sometimes to their own souvenirs. And apparently some of them would, when visiting Napoleon's house, just pull off a strip of the wallpaper to take away with them as a memento. And it was one of these souvenirs that had been preserved. Now, why did David Jones ask this interesting question, what colour was Napoleon's wallpaper? Well, he had the idea that the arsenic in the emperor didn't come from any poison put in his food or drink. He thought it may have come from the wallpaper. So they got this sample of wallpaper and they sent it for analysis. Now, this is a historic sample, so you can't destroy it. You can't take it and dissolve it in acid and test it by atomic absorption spectroscopy, because the owner's going to want the thing back. Now, one of the advantages of SEM-EDX is that it is non-destructive. You can analyze your sample and it's unaffected. Another advantage of SEM-EDX, of course, is that you can look at specific microscopic objects within your sample. And David Jones was particularly interested in the particles of green pigment on this piece of wallpaper. Now, why was he interested in green? Because in the 19th century, one of the commonest methods to get a good green pigment was to use a chemical called copper arsenite. And sure enough, when the green part of the wallpaper was analyzed by SEM-EDX, it confirmed the presence of arsenic. Now, if there's arsenic in the wallpaper, how does it get from the wallpaper to Napoleon? And the answer comes from the climate of St. Helena. St. Helena is subtropical, it's warm, it's humid, it's a great place for mold to grow. And some species of mold have evolved the capability to digest arsenic. So some of these molds are able to take arsenic and convert it into volatile forms of arsenic, such as arsine, which is a gas. So that is how the arsenic could have got from the wallpaper to the emperor. He could have breathed it in as he lay on his deathbed. So who killed Napoleon? Well, we have further evidence. We have the autopsy results, and the autopsy tells us that he died from stomach cancer. We also have eyewitnesses, because he was attended by his courtiers and his doctors, and some of whom wrote books and recorded what they saw. So who killed Napoleon? Well, it was probably stomach cancer, but his doctors certainly didn't help, because one of the standard drugs given in those days was the extremely poisonous compound mercury chloride. So we can't say that his doctors murdered him, but they certainly didn't do him any favors with the way they were treating him.